Welcome back to this next video in which we are discussing polynomial rings. Okay, so we've now created the set of symbols that we are going to use to create this polynomial ring over the commutative ring R. Okay, what we now need to do is define an addition and a multiplication law on this and prove that these addition and multiplication laws that we're going to define are actually going to obey the axioms of a commutative ring itself. Okay, so let's transfer this down to here. So first I'll just write out afresh the set of symbols that we have now created. Okay, so our ring to be the polynomial ring in the indeterminate x over the ring R. At the moment it's just a set of symbols, and it's the set that contains all these polynomials p of x, which are these things that look like sums, but remember they are just symbols. The sum from I is equal to 0 to infinity of ai x to the I, okay, where all the ai's are from the ring, capital R, and only a finite number of them are non-zero, so finite number non-zero. Okay, right, so there is our set of symbols. Now what we want to do is define the addition law firstly. Okay, so this is very intuitive. Okay, how are we going to define addition of two polynomials? Well, we're just going to do it component-wise and add the coefficients in the original commutative ring, capital R. Okay, so if I have one polynomial here, so it'll be the sum from I is equal to 0 to infinity of ai x to I, where we know that only a finite number of these ai's are non-zero and the rest are all going to be 0. Okay, and we want to add it to another polynomial, so we'll have the sum from I is equal to 0 to infinity of bi x to the I here. Okay, and if you like, we could call this polynomial ax, and we can call this polynomial bx. Okay, and now what we want to do is define what it means to add these two polynomials together. Okay, so we want to define what this symbol here added to this symbol is going to be, and we're going to use the fact that we know how to add elements of our original commutative ring R together. Okay, so the way that we're going to define this then is it's going to be the sum from I is equal to 0 to infinity of ai plus bi times xi, like so. Okay, so quite simply what you're going to do is add the coefficients. Okay, so writing this out explicitly, if we've got our polynomial ax here, which will be something that looks kind of like this, a0 plus a1x plus all the way up to, let's say, an xn, where n is the degree of ax. Okay, so this is ax, and then we'll have bx. So we want to add it to bx, so this is our polynomial ax. I'll just try and color code this a little bit. So here in yellow are all the different ways I've got of writing this polynomial, and then we're going to add it to our second polynomial bx here, which will be something of this form, b0 plus b1x plus all the way up to bmx to the m, where m is the degree of this polynomial bx. Okay, and quite simply what we're going to do is add component-wise. So we're going to add a0 to b0, we're going to add a1 to b1, okay, and this is all going to be done in the ring, capital R, the original commutative ring. So we're using the fact that we know how to add two elements of the original commutative ring together in that ring, okay, and we'll add those together to get some other element of the ring here, and that will be our coefficient in front of the monomial x to the I. Okay, so of course this is going to be another polynomial from this set, because only a finite number of these coefficients in the final answer here are going to be non-zero. Okay, because remember, only a finite number of these ai's are non-zero, only a finite number of the bi's are non-zero. Okay, so when we construct this thing, there is absolutely no way that we're actually going to somehow end up with an infinite number of coefficients not being equal to 0. Okay, so hopefully that's apparent. The utterly maximum thing that can happen, the worst case, is that all of the non-zero coefficients here are in front of different monomials to the non-zero coefficients here, i.e. for no monomial do you have a non-zero coefficient on both of them. They're all on distinct monomials from one another. In that case, the total number of non-zero coefficients that you'll end up with, non-zero terms that you'll end up with, will be the number here plus the number here, but that's the utterly maximum worst case that you can have. Okay, the most extreme case, I shouldn't say worst case, the most extreme case that you can have. Okay, so truly, you are going to have a finite number of non-zero coefficients here, and the rest of them will all be zero. Okay, so this will be back within our set here. Okay, so we've used the fact that we know how to add in our original commutative ring to define addition of these two polynomials together. Okay, and it is just component-wise. You just add the coefficients that are in front of each of the monomials. Okay, and that remains true even if the coefficient in front of a monomial in one of them is equal to 0. Okay, and of course we know that when you add the additive identity to another element of the ring, you'll get back that other element of the ring. Okay, so this is working very nicely here. Okay, so let's just make sure then that this addition law does obey the axioms that we need it to obey in order to be a ring. Okay, so remember, an addition law on a ring needs to obey the axioms of an abelian group. So we now need to check that if we define the addition on this set here in this way that I've just done, that it will actually obey the axioms of an abelian group. Okay, so let's now go over the axioms of an abelian group. So axiom number 1 is closure. This says that if I add one element of this set to another element of this set, I must get back another element within this set, i.e. you don't suddenly get something that's not in this set. Now I've just argued in favour of that. I've just shown you that the answer here will always be another element of this set, because these coefficients that you end up with will always be back in the ring capital R, and you will have a finite number of them that are non-zero, and therefore this polynomial that we get as our final answer, this will be back within our set. So we can tick off closure straight away. Addition is going to be closed. Okay, then axiom number 2 is associativity. Okay, so this concerns what if we want to add 3 polynomials together. Okay, we want it to be the case that it doesn't matter where you put the brackets. Okay, so let me write this explicitly out, so this might take up quite a bit of room. Okay, so if we're adding 3 polynomials together, so I'll write each one of them out. So here's one polynomial, the sum from I is equal to 0 to infinity of ai xi. Okay, and then we're going to have it being added to another polynomial, the sum from I is equal to 0 to infinity bi xi. And then we're finally going to have it added to another polynomial, ci xi, where I is going from 0 to infinity. And we want to check that it doesn't matter where you put the brackets, i.e. we want to check that if you put the brackets in this position, okay, so firstly add this polynomial to this polynomial, get the answer which is another polynomial, and then add that polynomial to this one. Okay, so that's what that means. We want to check that the answer that we'll find, the final answer that we'll get, will be the same as if we put the brackets in the turquoise position here, i.e. we firstly add this b polynomial to the c polynomial, get the answer which is another polynomial, and then add the a polynomial to that answer. Okay, so let's firstly consider what we'll get if we actually do it the purple way. Okay, so if we do it the purple way, we'll firstly add the a polynomial to the b polynomial, and we'll end up with this thing here. Then we'll add this polynomial to this polynomial here, the c polynomial. Okay, so how do you do that? Well, again, you just add components. So done the purple way, I hope you can appreciate that the final answer will be the sum from I is equal to 0 to infinity of coefficients of this form, ai plus bi, okay, plus ci, like so, and then all of that in front of xi. Okay, where this is now all done in our ring capital R. So this is addition in the ring, and this is addition in the ring. Okay, and the brackets are around ai plus bi. So you firstly add ai and bi together in the ring, and then the answer you add ci to get the final coefficient that's in front of each of the monomials. Okay, so that is if we do it the purple way, and hopefully you can probably anticipate what we'll now get if we do it turquoise way. Okay, so if we do it turquoise way, we will firstly add the b polynomial to the c polynomial, and we'll get something of this form. The sum from I is equal to 0 to infinity, but this time it will be bi plus ci times xi. Then what we'll do is we'll add this one, the a polynomial, to this, and again I hope you can appreciate that what we'll end up with finally is the sum from I is equal to 0 to infinity of ai plus bi plus ci, where now the brackets are around bi plus ci, so do those first. Okay, and then add ai onto that, and then multiply that by, or have that as the coefficient in front of the monomial xi. Okay, so this is what you'll get, the final polynomial that you'll get if you do it turquoise way. Now, why are those two things identical? Well, two polynomials will be identical if all of the coefficients in front of all of the monomials are the same. Okay, so let's have a look at the coefficients in front of the monomials in purple polynomial and compare them to the coefficients in front of the monomials in turquoise polynomial. Okay, well, we can see that those two things are going to be the same because all of these additions are done in our ring capital R, and in our ring capital R, addition obeys associativity, so this thing is going to give the same answer as this thing for all I that you can possibly come up with here. Okay, so indeed, it is going to be the case that all of the coefficients from the ring in front of the monomials in this purple polynomial will be the same as the coefficients from the ring in front of the monomials in this turquoise polynomial. So indeed, the two polynomials will be identical. Okay, so it does obey associativity. These two different ways of adding these polynomials do give the same answer. Okay, so we can tick off associativity. Okay, right. So, next axiom of an abelian group. The next axiom is that we need an additive identity. Okay, and I'll just now go over onto the other page. So axiom number 3 then of an abelian group is that there needs to exist an additive identity, an element in the set that will add to all other elements to give that other element back again, no matter what that other element is. Okay, so hopefully you can probably dream up such an additive identity. It's going to be the polynomial where you have the 0 coefficient in front of every single monomial. Okay, so it's going to be the polynomial that looks like this. The sum from I is equal to 0 to infinity of 0 times xi. Okay, so in front of all the monomials you stick 0. Okay, so we know that when we have 0 in front of a monomial, it's customary not to actually write that monomial out at all. So the way that this would actually be denoted is just by 0. So you'd only put 0 for the a0 term, so the term that's in front of x to the 0, i.e. in the constant portion. Okay, right, so this is how we denote this polynomial, and it's called the 0 polynomial. So where you've got 0 as your coefficient in front of all of the monomials. So this is the 0 polynomial. Okay, right. And this 0 polynomial will actually add to any other polynomial to give back that other polynomial. And the reason is, if we take the 0 polynomial, which is the sum from I is equal to 0 to infinity, 0 times xi, and we add it to any other polynomial, and you can do this either way round. I'll just do it this way round, but the argument holds exactly the same if you do it the other way round. So we'll have the sum from I is equal to 0 ai xi. Okay, the way we'll do that, just by definition, is we will add all of the coefficients together. So we'll do it component wise. We'll have 0 plus ai, and then xi, sum from I is equal to 0 to infinity. And of course, 0 plus ai, this addition is done in our original commutative ring, capital R. And when you add the additive identity to any element of the ring, capital R, you will get that element back again. So this coefficient here will just equal ai for all I from 0 to infinity, and therefore this polynomial will be exactly equal to that polynomial. So indeed, the 0 polynomial does add to any polynomial to give that other polynomial back again, and that will be true even if you do it the other way around. So if you flip these two around and do this polynomial plus the 0 polynomial, the answer will be exactly the same. So this 0 polynomial does indeed add to all the other polynomials to give that other polynomial back again. Okay, so we do have an additive identity. Next up, the fourth axiom of an abelian group is that we need additive inverses. Okay, so if I have some arbitrary polynomial in my ring, so here it is, ai xi sum from I is equal to 0 to infinity. So here's my arbitrary polynomial in my ring. Okay, and I now need to find an additive inverse for this. I need to find some other polynomial which, if this polynomial adds to that other polynomial either way round, will give me the 0 polynomial back again. Now hopefully again this should be pretty intuitive. I mean, we're not doing anything complicated here. The additive inverse for this polynomial here will be the sum from I is equal to 0 to infinity. And what coefficients are we going to have in front of each of the monomials? Well, we're just going to have the additive inverses of all of the coefficients that we've got here. So what we're going to have is the additive inverse of ai, where this is the additive inverse in our original commutative ring, capital R, and then that will be the coefficient in front of x to the I. Okay, so my claim is that this thing that I've got here is going to be the additive inverse for this polynomial from my ring of polynomials. Okay, so let's just check that this is true. So if I wanted to add these two together, the way I would end up doing it is I'd do it component-wise. And again, you can do this either way round, and officially you should check either way round that they give the 0 polynomial. But I will do it one way, and I hope you will agree that if I was to do it the other way, I would get the exact same result. Okay, so we will take our polynomial a here, and we'll add it to what I claim is the additive inverse of that polynomial in my ring of polynomials. And the way I will do that is I'll just add all the coefficients component-wise. So it'll be the sum from I is equal to 0 to infinity of ai plus the additive inverse of ai, where these two are being added together in my original commutative ring, and that will be the coefficient in front of the monomial x to the I. Okay, so this is addition in the original commutative ring, and of course, when I take the coefficient ai and I add it to its additive inverse in the ring, I will get 0, the additive identity in my ring, back again, and that's true no matter what I you're considering here. Okay, so you'll end up getting 0 in absolutely all the positions. In front of all the different monomials in your polynomial, you'll get the additive identity of our ring as the coefficient, and therefore that will become the 0 polynomial, i.e. our additive identity in this new ring of polynomials. Okay, so indeed all elements of the ring of polynomials do have additive inverses, and officially I should check that it's true the other way around. So if I take this and add it to this thing, so swap them round, that I get the same result. And of course that's going to be true because in the ring, if you add the additive inverse to the element, it doesn't matter which way round you do it, you'll always get the additive identity back again. Okay, right, so now the final axiom that I need to check for a abelian group is commutativity, axiom number 5. So I need to check that it does not matter which way round you add two polynomials. Okay, so I need to check that if I add the polynomial a here, so the sum from I is equal to 0 to infinity of ai xi, to the polynomial b, sum from I is equal to 0 to infinity bi xi, that I will get back it's the same as if I add them the other way round. So if I take the b polynomial, bi xi, sum from I is equal to 0 to infinity, and add it to the polynomial a, sum from I is equal to 0 to infinity ai xi. So I want to check that it really does not matter which way round you add two polynomials together. Okay, so let's just do the left-hand side, do the right-hand side, and show that the answers are the same. So if we do the left-hand side, we just do it component-wise. So it'll be the sum from I is equal to 0 to infinity of all of the coefficients added together in the ring. So it'll be ai plus bi, and that'll be the coefficient of xi here. And this addition will be done in our original commutative ring there. Okay? And then if we do the right-hand side here, this, again, we'll just do it component-wise, so it'll be the sum from I is equal to 0 to infinity, bi plus ai, where this is done, again, in our original commutative ring R. Now, of course, our original commutative ring, its addition was an abelian operation. It was commutative. So in the ring, ai plus bi is equal to bi plus ai, and I've missed off the monomial there, but never mind. I've corrected it now. Okay, so in our ring, as I was saying, ai plus bi is going to be the same as bi plus ai. Okay, and that's going to be true no matter what coefficient we're looking at, no matter which monomial's coefficient we're looking at. So for all I, that will be true. So what that overall means is that the coefficients in front of all of the monomials in these two polynomials will be identical, and therefore these two polynomials are going to be equal to one another, and therefore, yes, it really does not matter which way round you add two polynomials together, the answer will always be the same. Okay, so that was very, very simple. Addition is very, very simple in this new ring of polynomials that I'm creating. Multiplication is going to be slightly more fancy, but we'll go on to that in the next video.